Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Tuesday, September 22nd, 2020, which as I look over here is actually our 23rd day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at the do-nows and see what our schedule is for today. Today we're going to look at radioactive half-life and decay, and so you are picking up a chart of half-lives for various isotopes. Appendix 12, page 39 in your binder, and the radioactive decay assignment, which we're going to begin today. We're going to finish it tomorrow. So this is a part 1 and a part 2 lesson type situation. Yesterday we did lab 2-1. Remember, yesterday was an e-learning day, and you were to turn that in today. So that should be sitting on my desk if you're here at school, or if you're home, you should be submitting that to me at the beginning of your class period, whenever that might be, via email. So make sure you do that. Of course, the answer keys are posted here on the board and on my answer keys page in Canvas. So today we're going to continue the second part of Unit 2.2 on nuclear chemistry. We're going to go over half-life and decay, as I said a little bit ago. We're going to begin a homework assignment, which is page 40, numbers 1, 2, and 3 only. So we're going to cover 1, 2, and 3 only today. We'll hit the rest of it tomorrow. Also, you have your online homework assignment mastering over nuclear chemistry. I have just now opened that, and it is due this coming Friday, September 25th, by 7:30 a.m. this coming Friday. So don't forget about that. Okay, so let's get the board ready for the notes, and we'll get started. And there we go. All right, tilt that up just to here. There we go. So, quick review on what half-life is. We talked about this the other day. Basically, remember, a half-life is the amount of time it takes for a radioactive sample or isotope to be cut in half. All right, to be cut in half as it decays naturally. Remember, radioactive isotopes are very energetic and unstable, and they want to release that energy so that they can stabilize and become less radioactive. All right. So as an example I put up here, if we start with 1 gram of a radioactive isotope, after it undergoes 1 half-life, that 1 gram is cut in half to a half a gram. After it undergoes a second half-life, it would be cut to 1/4 of a gram, which would be 1/4 of its original amount. Okay, 1/2 times 1/2 is 1/4. After a third half-life, it would be cut in half yet again, down to 1/8 of its original mass or quantity. 1/2 times 1/2 times 1/2 is 1/8 of 0.125, and so on and so on. Now, if you look at this chart that you picked up today, Appendix 12, all right, this is the half-lives of some various radioactive isotopes. And as you can see, they vary greatly in the amount of time it takes for them to be, for their mass or quantity to be cut in half, or their half-life. Protactinium-234, as I say here in the notes, its half-life is only 1.2 minutes. All right, so every 1.2 minutes, it's being cut in half, so it reduces down quite rapidly. On the other hand, uranium-238, a half-life is 4.5 billion years. All right. Big difference there, right? One of the particular radioactive isotopes that we use in chemistry for a wide variety of reasons is carbon-14. Archaeologists, geologists, etc., rely heavily on the half-life of carbon-14 to provide accurate estimates for the dating of ancient once-living artifacts, in other words, carbon-containing artifacts, because the half-life of carbon-14 is known to be 5,730 years. Then, for instance, a wooden bowl found that shows a carbon-14 content of half that found in a current living tree would be approximately 5,730 years old. There are two methods for doing calculations involving radioactive half-life. We're going to do the chart method today. We'll look at the logarithmic method tomorrow. So let's take a look at the chart method. Let me scoop this up a little bit. So if you're solving for a quantity or a mass, we're going to check to see if the number of half-lives that have occurred is a whole number by using this equation. X equals T over T to the 1/2, where X is the number of half-lives that have occurred or transpired, T is the amount of time that has passed, and T to the 1/2 is the half-life time of that isotope, which again can be found on this chart or a chart similar to this that has other radioactive isotopes on it as well. If X is a whole number of half-lives, all right, then you can use the chart method. So if X is a whole number of half-lives, that number there is a whole number, then we can use the chart method to solve it. All right, so let's take a look at that. I'll advance the page. So, example 1. A sample of phosphorus 32 that has an initial mass of 50.0 grams. So that's our original mass, which we label as MO or M original. Okay. M sub O, I should say. What mass of this isotope will remain? So we're looking for the remaining mass, which is MR or M subscript R, will remain after 42.9 days. So there's the time that has passed. Now, from the chart, if I look up phosphorus 32, which is right there, all right, we can see that its half-life is 14.3 days. So T to the 1/2 is 14.3 days. Notice that the half-life time is in days. The amount of time passed must also be in days. All right, those time measurements have to match. They're units. If they don't, then we have to do a quick conversion to make sure that they do before we continue on with the decay process. Okay, just wanted to make that point. All right, so let's use our little equation here to see if we have a whole number of half-lives. So X equals T over T to the 1/2. So T is 42.9. T to the 1/2 is 14.3. And when you divide that, you get 3 half-lives. I'll reread that H-L, which is a whole number. All right. 3 half-lives. So since this is a whole number, we can use the chart method. Check. All right, so we can go ahead and use it. All right, so here's how we're going to set it up. As you can see, we call it the chart method because it's a chart. All right. So as you can see, we have 3 columns: number of half-lives, the time that's passed, and the mass remaining. So we start with the current time. All right, the initial time that the decay begins. So basically, we start at time 0. All right, time 0, no half-lives occurred. And our original mass then, the mass that we start with, in this case is 50.0 grams, all right? After 1 half-life, all right, the half-life time is 14.3 days. So what happens after a half-life to that original mass? It gets what? You said it gets cut in half. You're right, because that's exactly what a half-life means. Remember, the amount of time it takes for a radioactive isotope to be cut in half. It's quantity or mass. And so we're just basically dividing by 2 as we work our way down the chart here, okay? So this would be 25.0. Want to keep the recording of the data the same, okay? After a second half-life, all right, an additional 14.3 days would have passed, or 2 times the half-life, 2 times 14.3, which is 28.6 days. This gets cut in half again, to 12.5 grams. All right. We do a third half-life, which would be 3 times the half-life time, or 3 times 14.3. We are now looking at 42.9 days, which is, we've reached our end here. All right. We cut this in half again. We're down to 6.25 grams. Again, we're keeping the number of sig figs the same because we're dividing by 2 as we undergo each half-life. And so the remaining mass then to 3 sig figs would be 6.25 grams. How did we know to stop here? When we reach the amount of time that's passed that's listed in our problem, we know we're at the end. Okay, so that's as far as we need to go. We didn't need any of that down there. Okay. All right. Let's look at another one. At the present time, a piece of petrified wood is known to be 22,920 years old. So that's the amount of time that's passed since it originally began to decay, and contains 4.00 grams of carbon-14. So that's now. That's now, not originally. So that is the remaining mass. All right, the remaining mass. What mass of carbon-14 was in the wood originally when it died? All right, so we're looking for the original mass now, the original, okay? If I look up carbon-14 on the chart here, I think we mentioned it earlier, but I'll double check. There it is, right at the top of the chart, 5,730 years. So T to the 1/2 is 5,730 years, okay? All right, let me raise this up, and then we will continue on with the chart so we can see it better. All right. So again, this was the time that had passed, 22,920 years. This is the remaining mass, 4.00 grams. We're looking for the original mass. And again, the half-life time for carbon-14, 5,730 years. So get that back filled in. All right, so as we look at our chart here, this is the original mass. We don't know that yet. All right, we're going to work our way towards that. So let's do our little equation here and see how many half-lives were involved here. So we have x equals t over t to the 1/2. Remember, x is the number of half-lives. T is 22,920 years. The half-life time, 5,730 years. Those are in the same unit, so that we're good to go there. And again, this comes out as a whole number, all right? Which means then that we can use the chart, all right? So we got 4 half-lives. I'll put a little check there. We can use the chart, so we will. Now, we know then that we're going to go 4 half-lives. We know that for a fact. So I'm just going to go ahead and go 1, 2, 3, 4 right there. All right, we already know that. Just like before, we knew we were going to go 3 half-lives and no further. Okay, so the half-life time, which is 1 half-life, all right, is 5,730 years. A second half-life would be twice a half-life time, or 2 times 5,730, which then would be 11,460 years. Our third half-life, which would be 3 times the half-life time, or 3 times 5,730, is 17,190 years. And a fourth half-life, which would be 4 times 5,730, gets us to 22,920 years, which is exactly our number right there. So we know we've done it correctly mathematically. We're where we need to be. Now, we're going to take what we're given up here. It says we have 4.00 grams remaining after this 22,920 years has passed. So that 4.00 grams goes down here in half-life 4 next to 22,920. Now, think about this. So when we started up here and we underwent half-lives, what happened to the mass or the quantity? Well, it cut in half every time we went down the way. What do you think we're going to do when we go up the way in the opposite direction? Instead of dividing by 2, what are we going to do? If you said multiply by 2, you're absolutely right. That's exactly what we're going to do. So now we're going to work our way back up here, and we're going to end up with the original, which is what we're looking for. So 4.00 times 2 is 8.00. I'm keeping the sig figs the same here. And we're multiplying. Times 2 would get us to 16. I'm going to do 16.0 to keep us at 3 sig figs. Next one, 32.0 grams. And finally, one more time, gets us to our original mass, which would then be 64.0 grams. So our original mass then would be 64.0 grams. Okay, again, 3 sig figs, keeping it the same as the mass that we were starting with. Okay, all right, and I believe, nope, one more. Go to the next page. Thought there was no. Yeah, because we got to talk about if we're solving for time. All right. This time we were solved. The first two we solved either for the remaining mass or original mass. Now we're going to look and see what we do if we're solving for time. If you're solving for time, check to see if the amount or mass has reduced by a factor of 1/2. That's the key in being able to use the chart method involving time. All right, a factor of 1/2. Because remember, after every half-life, the original mass or the original quantity is cut in half. So here's where you kind of got to know your fractions in relation to 1/2, which would be, 1 half-life is a 1/2, 2 half-lives is a half times a half, or 1/4, 1/8, 1/16, 1/32, etc. If percentages are used rather than fractions, then you need to know your corresponding percentages to your fractions of 1/2. 1/2, of course, is 50%, or 0.50. 1/4 is 25%, or 0.25. 1/8 is 0.125, or 12.5%. 1/16 is half of that, which is 0.0625, or 6.25%. 1/32 is 0.03125, or 3.125%, etc. So hopefully you remember your percentages in relation to fractions of 1/2. All right. Now, if x then is a factor of 1/2, then we can use the chart method. Now we're going to use a similar equation to what we did before with time, only now we're going to do it related to mass. So now we're going to use x equals the remaining mass over the original mass. If that number there, when dividing those two, is a factor of 1/2, then we can chart it. Okay, then we can chart it. So this is the equation we're going to use right here to determine that. So let's do one like that, and then I think we're done for today's lesson. So we have here, let me erase that. We have a sample of cobalt-60 that is used for cancer therapy. Okay, so if any of you had friends or relatives who have undergone chemo, my mother did, cobalt-60 is a very common radioactive isotope that's used in fighting cancer. In fact, cobalt-60 is exactly what they used in treating my mom's cancer. If a sample of cobalt-60 that's used for cancer therapy has an original mass of 40 grams, that's our original, MO, and is stored on a lab shelf in a hospital, how long will it take? So we're looking for T now, for the mass to be reduced to 5 grams. So that's our remaining mass, 5 grams. All right, well, let's see if this is a factor, this reduction in mass is a factor of 1/2. So we're going to take X now equals MR over MO. Our remaining mass is 5.00. Our original mass was 40.0. And that comes out to 0.125. All right, which, if you recall, is 12.5%, which is equivalent to 1/8, the fraction 1/8. And 1/8 is, all right, a factor of 1/2. All right, it is. So since this is, since 1/8 is a factor of 1/2, we can use chart method. Check. All right. So let's go on now to this. All right. So cobalt 60, need to look that up. Cobalt 60's half-life time is 5.26 years. So T to the 1/2 equals 5.26 years. Again, that comes from the chart, the appendix 12 that you guys now have. All right, so let's see what we got here. We know that we're starting out with an original mass of 40 grams, 40.0 grams. And we know we're going to end up with 5 grams. So let's start with the mass, and we'll work our way down that column first. So again, as a half-life occurs, that mass is going to get cut in half. So after one half-life, that's going to cut down to 20.0 grams. After a second half-life, it's going to be cut down to 10.0 grams. After a third half-life, it's cut in half again, and keeping it at 3 sig figs, 5.00 grams. So if you notice, we have achieved our remaining mass. So we know to stop there. We know then for a fact that we will have undergone 3 half-lives. Okay? So now, let's go to the time passed. So 1 half-life is the half-life time of cobalt 26, or cobalt 60, sorry, is 5.26 years. All right. A second half-life would be 2 times 5.26, which would be 10.52 years. Our third half-life would be 3 times the half-life time, or 3.526, which would be 15.78 years. And so it asks for this time right here. Given that our data here is in 3 sig figs, we're going to want to round that to 3 sig figs. So T is 15.78, which would then be 15.8 years. Again, keeping our data at 3 sig figs as it's been presented. All right? So 15.8 years would be the correctly rounded answer. And that, my friends, is the chart method regarding radioactive half-life and decay. So, again, your assignment for tomorrow is to do numbers 1, 2, and 3 only. And then we will pick up our lesson tomorrow, and I will teach you how to use the logarithmic method, which must be used if our time that is passed, all right, does not yield us a whole number of half-lives, or if the reduction in mass is not a factor of 1/2. If those aren't true, then this method cannot be used, and we're going to have to learn how to do it logarithmically. We'll hit that tomorrow. So for that, this is Mr. Keister signing off for today. Everybody stay safe, keep working hard, and I'll catch you next time. So long.